Okay, let's look at question 5 from November 2017, reaction rate. A group of learners uses the reaction between powdered zinc and excess dilute hydrochloric acid to investigate one of the factors that affects the rate of a chemical reaction. The balanced equation for the reaction is zinc plus hydrochloric acid goes to zinc chloride plus hydrogen gas. They conduct 2 experiments. The reaction conditions used are summarized in the table below. The results obtained are shown in the graph, not drawn to scale. Okay, so let's have a look here. The temperature is the same, the volume of acid's the same, the concentration of the hydrochloric acid is different. So this is what we are changing. This must be our independent variable, is the concentration of hydrochloric acid. Okay, let's go on and have a look at the questions. Define reaction rate. The change, make sure you write the change in concentration of products or reactants per unit time. So make sure you have per unit time and make sure you have change. Write down an investigative question for this investigation. Now, every time we write down an investigative question, we have to make sure we have an independent and a dependent variable. So as the researcher here, we are changing the concentration. So we need a question, and it's a question, so it must be a question that we can have an answer and end in a question mark. It's not like state the hypothesis where you must make a statement. This is a question. So our question is going to involve how does the concentration of hydrochloric acid and what are we testing affect the reaction rate or affect the production of products over time. But let's just use reaction rate. So how does the concentration of a reactant, okay, so this way if we do this we're covering all our bases. So we go hydrochloric acid, let me write it out in full, hydrochloric acid. How does the concentration of a reactant, hydrochloric acid, affect the rate of reaction? Okay, so how does the concentration of a reactant affect the rate of reaction? If we didn't want to say rate of reaction, we could say how does the concentration of a reactant affect the production of hydrogen gas per unit time? That's a very specific investigative question, but this one should work. Okay, so now which curve, P or Q, represents the results of experiment 1? So let's look at the curves. P has a very steep gradient. We are producing hydrochloric acid really fast. This reaction has gone to completion in 30 seconds. And in Q, it's only gone to completion in 45 seconds. So Q has a slow reaction rate. P has a fast reaction rate. So we can expect P to belong to the concentrated acid and Q with the slow rate to belong to the less concentrated acid. So experiment 1 was the more dilute acid. So we're going to say curve Q. Okay. Q represents experiment 1 because Q has, what do we say, less steep, because Q has a less steep slope, showing a slower reaction rate as is expected in experiment 1 because experiment 1 has a lower concentration of acid. Okay, so that's why we picked the one with the less steep slope. We should actually say here because the slope of Q is not as steep would be better English, but you get the picture. Okay, the average rate of production of hydrogen gas as represented by graph P was 15 cubic centimeters per second. Calculate the mass of zinc used. Take the molar gas volume at 25 degrees to be 24,000 cubic centimeters. Okay, so look here first of all. 15 cubic centimeters per second was the average rate here. Okay, so this average rate, when you find the average rate of any graph, that's when you go from one point to the other point and you just draw a line across them and you find the average steepness of this curve. So if you've got the average rate, it's from 0 to 30. They drew a line across there. So we need to convert this average rate. You see, we don't know this volume of gas produced, but by reversing the average rate, by using the formula for average rate, we can actually find the change from 0 to here. Okay, look, let me show you. So rate of reaction is equal to the change in concentration or the change in volume. We can just, you don't actually have to put concentration, it's the change in volume of the products, okay, over, and you know I'm using divide for over the change in time, okay. So they said to you the average rate of reaction, and this is in cubic centimeters, so my answer is going to come out in cubic centimeters. So my rate of reaction is 15 is equal to the change in volume of products, which is what we want. The change in volume of the hydrogen, okay, divided by, what was the time? From the graph, the average rate was determined from 0 to 30. So this is, we should actually show the 0 here, 30 minus 0, okay. So now by that thing algebra, okay, it's going to be 15 times 30, because 30 minus 0 equals 30, equals the volume final minus the volume initial, okay. So 15 times 30 I think is 450. I hope you're using your calculator. So this is going to be the volume final minus 0. So 450 cubic centimeters is the final volume of hydrogen. Okay, I hope you're all with me how I worked that out from the slope of the curve and the reaction rate formula. So now we've got the final volume of hydrogen. It doesn't do us any good knowing a volume because we need to know moles. We always need to know moles, and this says take the molar gas volume to be 24,000 cubic centimeters. So we're going to go, the number of moles of hydrogen is equal to V over Vm. Make sure you write the formula. You remember this formula. It's the normal stoichiometry formulas that we use. And so my volume is 450 over, what did it say it was? Vm, 24,000. So remember that if you're at room temperature, it's warmer than STP, so the gas is expanded, and that's why we're using that number and not the number in the data sheet at the back. So according to my calculator, I've got 0,01875 moles of hydrogen. Okay, so did we get asked to find the hydrogen? No, we didn't. We got asked to find the mass of zinc. So we need to have a look here. The mass of zinc is not in the question. We need to have a look at the balanced equation here. Okay, so what is the relationship in the equation between hydrogen gas and zinc? They both have a coefficient of 1. So the mole ratio of hydrogen to zinc is 1:1. So this reaction used 0,01875 moles of zinc. Okay, so that's perfect. The moment we found the moles of zinc, we can find the mass of zinc, because you remember N equals M over M. So now the mass of zinc is going to be equal to, write the formula, the number of moles times the molecular mass. Where are we going to find the molecular mass? On the periodic table. So the number of moles, 0,01875 times, what's zinc on the periodic table? Zinc is 65. So let's do this on our calculator. I've got the number of the mass of the zinc is 1,22 grams. No unit, no mark. Okay, so there we go, we found the mass of zinc. In a third experiment, 200 cubic centimeters of 0,25 molar dilute hydrochloric acid solution at 35 degrees reacts with the same amount of zinc powder as in experiment 1 and 2. Okay, so look here, 35, the questions all got 25. So we've now done the same reaction as experiment 1, but we've increased the temperature because check, it's the same concentration as experiment 1. Will the heat of reaction compare to experiment 3? Heat of reaction will be equal to, because the only thing that changes the heat of reaction is changing your reactants. Okay. How will the activation energy of the reaction in experiment 1 compare to that in experiment 3? Choose from more than, less than, equal to. Here your answer is exactly the same. It's also equal to. Why is it also equal to? Because the only thing that's going to change the activation energy is a catalyst. Okay. Now it says to you the rate of the reaction in experiment 3 is higher than that of experiment 1. This is not a surprise. Experiment 3 is hotter. Fully explain this statement by referring to the collision theory. Okay, so collision theory, whenever we talk about collision theory, we must talk about effective collisions, number of particles, and whether we are increasing or decreasing the rate of reaction. Okay, so now let's explain this nicely. Okay, experiment 3, how did they write 3? Experiment 3 is at a higher temperature than experiment 1. This means that more particles, this means, okay, let's first say that the average kinetic energy of the particles is greater, which also means that more particles have activation energy or more than activation energy. This means that there will be more successful collisions, sorry, not successful, effective, forgetting my science word. There will be more effective collisions per unit time. Make sure you put the per unit time. There will be more effective collisions per unit time, which will increase the reaction rate. Okay, so you're going to get a mark here for explaining that there's more particles which have the activation energy or greater. You're going to get a mark for saying there are more effective collisions per unit time, and you're going to get another mark for saying the reaction rate has increased. Well, I know that's said over here, but they must all go together into this 1, 2, 3 thing. You should look at the memo, but make sure you have effective collisions, make sure you've referred to how many particles have activation energy, and make sure you state this is going to increase the reaction rate.